In this lesson, we are going to write the program that we wrote for the drill press again, but this time, instead of using the set and reset instructions to latch the output, we're going to use flip-flops. The flip-flops are in the BitLogic folder here. As you can see, we have two types of flip-flops, the RS flip-flop and the SR flip-flop. The operation of these two instructions is similar to the operation of the set and reset instructions, except that here in the flip-flops, we have both set and reset instructions within one block, and we can use them together. For instance, in the RS flip-flop, if we energize the reset input, the flip-flop output will be false, and if we energize the set input, the output will be true. So the set and reset instructions are situated together in flip-flops. From the point of operation, RS and SR flip-flops work exactly the same, with one slight difference. In these instructions, the lower input always takes priority over the higher input. Now, what does that mean exactly? Well, it means that if we energize the two RS flip-flop inputs simultaneously, the set input has priority, and as a result, the output will be true in this example. But if we energize both of the SR flip-flop inputs simultaneously, the output will be false. Why? Because here, the reset input has priority over the set input. So, depending on the kind of operation our process needs, we can use either an RS or an SR flip-flop. Okay, now let's see how to write the program. As you know, our drill press has 3 inputs and 2 outputs. We learned earlier how to assign a symbolic name to an address, so from now on, we're going to use symbolic addressing instead of absolute addressing. So in the OB1, we open the symbol table from the option menu. Now, let's select some symbolic names for the addresses. Drill start for IO0, pump start for IO1, stop for IO2, drill for output address Q40, and pump for Q41. Now, we'll enter these symbolic names here one by one. After we're done with the table, we save it and navigate back to the OB1. As you know, when the drill start is pushed once, the drill will be turned on continuously, which means we should latch this output. In the program that we first wrote for this machine, we used the set instruction for this purpose, but here we are adding an SR flip-flop. Okay, we place a simple coil in the flip-flop output and assign it the address of the drill. Now to energize the drill, we can place an open contact here for the drill start. Now, when the switch is pushed once, the drill output will be activated continually. Now what can we do to turn off the drill? Well, we can place a close contact on the reset input and assign the address of the stop switch to it. Okay, so far we have created a program to turn the drill on and off. But as you can see, we still have some red question marks telling us that we need to enter an address here too. So what is this address about? Well, when drill start is pushed here, we expect the flip-flop to make the output true and keep it true even if the set input is not energized anymore. The flip-flop needs 1 bit of space to keep the output true, so we should enter the address of the bit here on the top of the flip-flop. For instance, we can enter the address of MOO here, but if we enter the address of the drill output here, it works fine as well. So here the flip-flop reserves the bit number 0 from byte number 4 of the PIQ as a memory bit or space to store the output and keep it true. Okay, we need a similar program for the pump output. So, to make things a little faster, we can copy this network and paste it here. and then change the addresses of the input and output to the pump's input and output addresses respectively. Because we want both outputs to be de-energized simultaneously when the stop switch is energized, the stop input is common to both the drill and the pump outputs. Okay, we're almost done with the programming, but there's a small change to make. We want to prevent the pump from activating while the drill is still turned off. So, we can place an open contact here, and as we did in the previous program, give it the drill's address. Now we can test the program by saving it and downloading it to the CPU. Okay, as you can see, when the pump start is pushed, the pump won't turn on now because we don't have the drill turned on yet. Now we push the drill start, and as you can see, the set input is energized, making the output true. Now, if we remove our hand from the switch, you can see that the output remains true. Here, because the drill's open contact is true, when we push pump start, the pump will be turned on. To turn off both the drill and the pump, we only need to press the stop switch once. Okay, so the program works exactly as we want it to. Now, let's energize the stop switch and then energize the drill start switch as well. Here, as you can see, when both the set and reset inputs are energized, the output is false. This confirms that the reset input in the SR flip-flop always takes priority over the set input. Okay, in this lesson, we learned about the function of the flip-flop through a practical example. In the next lesson, we're going to learn how exactly the CPU processes our program. This can make both writing and troubleshooting programs easier and more understandable processes.